So now our job is complete. Let's open the output file in ChemCraft. So now if I try to see the thing, the bond length is 1.199. Let me write it as gas. The CH bond length is 1.107. And HCH angle is just to make sure that I am not doing any mistake 116.039 116.04. About the frequency, can write it here. It's 1201 1267. We have discussed already the nature of the things. 1533 1818 2880 and 2936. Now to do a PCM calculation on the top of it, what I can do is I can start with the formaldehyde gas input file, and then I can write CPCM water Remember, I told that it's always a good idea to start with the gas phase optimized geometry. So, I will use the XYZ file as 0, 1, formaldehyde gas dot XYZ. It's formaldehyde dot PCM. I believe we have saved it as we want it to formaldehyde.pcm.inp. Formaldehyde underscore PCM So, now the PCM job has been done. It will be a good idea to open the PCM output file and see it line by line. So, the standard ORCA information, optimize coordinate set, geometry pole, shark, DFT gate grid, cosec grid. Here comes the ORCA solvation model. So, I am using water. It's So, epsilon value is 80.138, the refractive index. So, basically the surface type, it's a Gaussian, discretization scheme, charge density, epsilon function CPCM. You can also see to COSMO and all the other options. So, this is the extra time taken for CPCM. So, after the gas phase calculation, these are standard gas phase calculation. So, this is surface charge, this is corrected charge, outlying surface charge, and this part, this free energy cavity plus dispersion, this is not currently implemented in the current solvation scheme. So, to include that, you need to go to different models. We will come into that when we will discuss about free energy of solvation. So, this is how the optimization was done. Now, let us open it with the Chemcraft and see how the bond length and the air frequencies has changed. Let us close it. Now, for CO bond length is 1.2065. So, the CO bond length has increased 1.206. One point 102. So, CH bond actually reduced a little bit, 1.102, not so much. 1.103 actually, to be honest. Now, let us see the angle. It is 116.45. Now, let us see the frequencies. It's 12.17. So, this is H bond stretching. So, my bond length has reduced. So, my frequency has increased. So, this correlates. It's 12.64. 1526. Now, you see this one, CO stretching. My CO bond length has increased, and so my CO stretching frequency, because the bond has become weaker, so the CO stretching frequency and see has reduced. And this happened for the other two frequency, 2920 and 2991. So, if I now want to, calculate the shift, so this is how the shifts are. In certain cases it has increased, in certain cases the frequency has decreased. So, we have just discussed about how the effect of solvation actually changes the bond length and frequency. Now, if you want to calculate the solvation free energy, so my change in the solvation free energy due to the PCM model is actually written as a combination of 4 terms. So, the first term corresponds to the energy difference between the liquid phase expectation value of the gas phase Hamiltonian and the gas phase potential energy surface, and the corresponding value for the gas phase, and that is written as ERL minus ERV. The second term accounts for the electronic polarization contribution to the del G solvation and is calculated from the charges spread over on the surface of the solute cavity. The third term is a cavitation energy, and that is the reversible work required to create a cavity inside the bulk of the solvation in order to accommodate the solute, while the last term, the delta G dispersion, accounts for the change in the dispersion energy occur when the solvating the solute, and some of these last two terms correspond to the non-electrostatic contribution. So, in the normal PCM model, currently ORCA does not implement these two corrections. And if I go back to the output file, we'll see that if you go to the first part, if you come after the SCF, you will see that the free energy cavity dispersion constant is not implemented here. So, ORCA cannot take care of that term. If you go to the end also, it is just the normal free energy correction scheme. This does not contain the cavity and the dispersion scheme, and so you need to use special techniques for calculating this one. One of them is the SMD solvation model by Kramer and Truller group, and it is based on the quantum mechanical charge density of the solute molecule interacting with the continuum description of the solvent. In the model, the full solute electron density is used without defining partial atomic charges, and the solvent is not represented explicitly, but rather a dielectric medium with the surface tension as the solute solvent boundary. SMD is an universal solvent model in the sense that it is applicable to any charged or uncharged solute in any solvent or liquid medium for which a Q descriptors are available, and in this particular the descriptors are dielectric constant, refractive index, bulk surface tension, acidity and basicity parameters. This model separates the observable solvation free energy into two main components, the del G NP and del G CDS. So, the first component is the bulk electrostatic contribution arising from the self-consistent reaction field treatment that involves the electrostatic interaction using the CPCM model. Only the radii are set to intrinsic atomic Coulomb radii, and the second component is called the cavity dispersion solvent structure. This is the contribution resulting from the short range interaction between the solute and solvent molecules in the first solvation cell. So, these interactions are not included explicitly, but they are parameterized in such a way that this effect automatically comes. So, these are the parameters in the ORCA for if you want to get the SMD method. In most of the cases, it is fine to include the SMD solvent is equal to water, but a much better solvation model in most of the cases is the COSMO method. So, COSMO is conductor like screening model by Andreas Klamt, and that is considered as one of the most accurate solvent models. In principle, they are like a CPCM model with a different value of the epsilon. So, you can use the COSMO epsilons in the CPCM by using CPCM C keyword. So, after the CPCM, you just add another C that will use the epsilon corresponding to the COSMO, but the more interesting thing is to use the COSMO-RS, what is the real solvent that combines COSMO. So, COSMO only gives you the electrostatic part. The COSMO-RS combines the COSMO with statistical thermodynamics to predict thermodynamics properties like solubility, partition coefficient, free energy, and ORCA is interfaced to open COSMO-RS, which is an open source implementation of the original COSMO-RS model of Andreas Klamt, and this model is widely used in both academia and industry to predict fluid phase thermodynamics. And you can ask for this calculation by giving the keyword COSMO-RS and in the bracket solvent. So, why I am using cyclohexane here? That is the next example where we are going to calculate the free energy change from the transfer of acetamide from cyclohexane into water, and we are going to use the semi empirically parameterized DFT method R2 scan 3 minus C for doing the optimization as well as the single point calculation. So, to do that, what we should do, first we draw the structure optimize them in the gas phase, and this is a neutral molecule, so it's not so the change in the structure will be quite small from going from one solvent to the other. If you have a charged molecule, then or bonds which are more prone to solvent induced corrections, there you need to optimize the structure in that particular solvent. But in this case, what we will do is that we will optimize the structure in gas phase and then do the COSMO-RS calculation in the two different solvent as a single point calculation, and then calculate what is the energy difference. So, let us first start with the drawing the structure. So, let us use Avogadro. I can include an acetaldehyde. And I can add a nitrogen here. I can calculate opt. Maybe I should make a different folder. Solvation. Solvation G. Okay, I should have acetamide dot gas phase Let me run the calculation now.